Well, hello everybody, it's Dave here, and today we're going to do a lesson on this idea of static and dynamic equilibrium. If you've taken a chemistry class before, you've probably heard of equilibrium in terms of a chemical equation, and this is going to be similar in that there's going to be this balance associated with equilibrium, except in this case we're going to be dealing with the idea of forces and the idea of torque. So when we speak of mechanical equilibrium, the first thing to recognize is it doesn't have to be stationary. The key statement to be made about equilibrium in physics is the idea that it's not accelerating. So we could either have the center of mass being static or stationary, or we could have it moving at a constant velocity so long as the net force on it is equal to zero. Now, when we're talking about not accelerating, there's really two accelerations we were referring to. First and foremost, we're talking about the translational acceleration, meaning that it's not accelerating left or right or up or down. At the same time, we're also making sure that it's not rotating, which means it's not accelerating angularly, and when we refer to that, we're going to talk about it in terms of clockwise or counterclockwise. So the first condition of equilibrium is this idea known as translational equilibrium. And when you studied Newton's laws and dynamics, we learned that, according to Newton's second law, if a net force is present, an object will accelerate. Well, that also implies that if there is no net force present, then the object will not accelerate. It will remain at whatever motion it's going at. That is exactly what this is stating here, is that there is no net force because, as we said before, for it to be in translational equilibrium, it can't be accelerating left or right or up or down. And so we write this in an equation as the sum of the forces is equal to zero. And if we actually took those forces and broke them down into a horizontal direction or a vertical direction, or in general the idea of x and y, then the sum of those forces would also have to be zero. And though we speak of this as one of the conditions of equilibrium, it is not in itself sufficient to be in complete mechanical equilibrium, because as we said before, not only can it not be accelerating left or right or up or down, but it also can't be accelerating in an angular direction, meaning clockwise or counterclockwise. So this picture here is a common setup for a translational equilibrium problem. We're not 100% sure what this is because we have no context of the problem, but if you can see the directions, up and down is related to the y direction and left and right is related to the x direction. So this could be something like a block being hung by two strings and its weight matters. Well, if we know that it's in translational equilibrium, then we know that the components in either x direction and y direction have to be equal to zero. And so if we take a look at it that way, we can see that the x component of Fc has to be equivalent to the x component of Fa, as there is no other forces pointing in the left or right direction. At the same time, if we're talking about the vertical direction, we know that W is pointing straight down, which is the vertical direction, and that has to be equivalent to the sum of the two y components of Fa and Fc, since this thing is also not accelerating up or down. This is a classic case where we're dealing with components to end up with our equations to solve. At the same time, when we're dealing with a translational situation, we could also take the forces and literally take the sum of them. And if you notice with the diagram on the right, we can see that the arrows are pointing in basically a clockwise direction. And this should make sense if we think back to the way that vector addition works, is the fact that if we take the sum of those three forces, where W is pointing is exactly the origin where Fa started, which means that the net force of this particular system is equal to zero. The benefit of dealing with it in this method is instead of dealing with components in the x and y where we may have an arithmetic error, in this case we could actually apply something like the sine law or cosine law and really deal with this non-right triangle in a much more direct way. And it depends upon the method that you wish to solve. I always like using the simplest method, and sometimes the simplest method involves a little more complex math. The new quantity that you may have heard of before but have never defined is this concept of torque. And as we said before with the conditions of equilibrium, we have to have it in translational equilibrium such that left and right and up and down, the sum of the forces there equal to zero, but at the same time it can't be accelerating in an angular direction, meaning that it is not rotating. Or if it is rotating, it's not rotating in an accelerated fashion. Well, when that's the case, what we say is that the net external torque must be equal to zero. And so if you see this equation down here, the sum of the torques is equal to zero, where tau, the Greek letter tau, is representative of this idea of torque. And so to begin our discussion of torque, I want you to imagine looking down on the top of a door. And you can see that on the left side, we have what we've labeled as O, or the origin, and that's going to be the hinge. We have this vector called the position vector measuring from the origin to the doorknob, and then we have a force that is perpendicular to this position vector, pointing in the direction that we would want it to go. So if we think about this just in pure experience terms, we know that if we applied a force forward, this door would rotate to the left or counterclockwise. And so it makes sense then that we put the doorknobs on the end of a door for a reason. You'll notice that you don't see a lot of doorknobs that are close to the hinge or in the middle of the door. And the reason for that is because there really are three factors that affect the torque that you can impart upon an object. And these three ideas are the magnitude of the force itself, the position of where you're applying that force, and the angle at which it's applied to. You'll notice that with this diagram, we've dealt with it being perpendicular to the door, but if we pushed on an angle in or outwards, we would still achieve the goal of opening the door, but we wouldn't necessarily maximize the torque or the ability for this door to rotate. So just so we're clear, when we're talking about the position vector, what we're doing is we're drawing a vector from the origin point to wherever the force is applied. When we deal with the actual calculation of torque, we're only going to use the magnitude of this position vector. But if we go to a general definition of what torque actually is, then this position vector and the way in which it points will be important to that math. So it's important to recognize that we're typically going to deal with the magnitude, but the actual direction from the origin to that point of interaction with the force, that's going to matter a little bit down the road. The other thing to recognize too is the first example with the door is we applied a force that is perpendicular to the door, i.e. perpendicular to the position vector. But at the same time, we know that we don't always have to apply that force perfectly perpendicular, that it could be on some angle, and despite it being on the angle, some of the force in which you're still applying to the doorknob is going to result in that motion. So if we take a look at a picture that accentuates what I'm just saying, if you look at the picture at the top here, well, this is obviously somebody that doesn't know how to open a door. Because if you put an applied force on the doorknob and you point it directly parallel to the door, there will be no resulting motion. Now, if you're strong enough, you might be able to pull the door off the hinge, but I don't think that that's the goal of your force. Conversely, if we take a look at the picture below, we can see that there's a force being applied on an angle. And although all of that force is not going to be directed in the direction of motion that we're hoping for, which is a rotation in a counterclockwise direction, some of that force actually will. We can see that this force could be split up into two components, namely F cos theta, which would be the parallel component, and F sine theta, which would be the perpendicular component. And it's only going to be that perpendicular component that's going to result in the rotation of the door itself. So what this means is we have a more general definition of what torque actually is. If we understand that the only way to cause a door to rotate, or any object to rotate, is to apply a force that is perpendicular to that object, then even when we have a force that is on some angle, we can find that perpendicular component, and that will be the amount of force that's being applied to cause a torque to occur. So torque, by definition, is the tendency of a force to rotate an object about some axis, where tau is equal to RF sine theta. Now this sine theta is very important because now we know that if theta is equal to 90 degrees, the sine of theta is equal to 1, and what we're left with is a more classic version of this equation, which is tau is equal to RF. Now if you Google torque, you might find it sometimes listed as force times distance, or the applied force times distance, and that is certainly going to be the case in a lot of cases where the applied force is perpendicular to the object. But as you'll see very shortly, this convention of RF sine theta will be something that makes a lot more sense when you see the general equation for torque. Now within this equation, I hope you can see that the units for torque are Newton meters. F is obviously a force, and R is going to be the length of that position vector. So again, even though we're defining it as a vector, we're only going to use the magnitude, or the distance actually from the pivot point or the origin point to the applied force, and that's going to be what we use. Theta is going to be our angle between the force and position vector. The most important thing to remember here is we're just finding the component of force that is perpendicular to the object that we're trying to rotate itself. Now, when we come up with the direction of torque, it's important to recognize that torque is itself a vector quantity. However, when we're actually calculating torque, what we're doing is we're dealing with a position vector and doing some math with it involving another vector that is perpendicular to that position vector. Because of this, finding the actual direction of torque can be a little tricky because it doesn't quite make sense in our current understanding of dealing with vectors that we would just say that it is in the direction of force. And the actual answer to the direction of torque is actually along the rotational axis of the object itself. And so if we're referring to something as rotating counterclockwise, we're going to call that a positive torque. And if we're turning in a clockwise direction, we're going to call that a negative torque. Now, this can be a little confusing, but what we have here is something known as the right-hand rule. And in general, torque is actually equal to R cross F. And this cross idea here is in mathematics known as the cross product, which is essentially taking the vector product of R and F. So this is where I said the issue lies, is the fact that we're doing some math with two vectors, and all we're really trying to tell you here is in grade school, when we taught you that multiplication is using a cross, we were lying to you, my friends. That was actually a dot product. So for those of you that move on to linear algebra, I'm sure you will recognize the difference between the two quantities. Now, what that means, though, is when we're dealing with the cross product of vectors, we can actually use our right hand to represent the direction of the resulting cross. And so if torque is equal to R cross F, what we do is we take our fingers and we point them in the direction of the position vector. And so with this wrench, your hand should be parallel to that wrench, and your finger should be pointing up and to the right. And then to do the cross, what you do is you take those fingers and you curl them around. So I'm actually curling them in a counterclockwise direction so that my fingers are pointing now in the direction of F. I haven't moved the bottom of my hand, and what your thumb should be doing right now is pointing directly at you. And what we're saying is that when we define the direction of torque, that thumb direction is going to be considered a positive torque. So when the resulting rotation of the object is going to be counterclockwise, we're calling that positive. If you flipped it around now and had force going in the opposite direction, you would actually have your thumb pointing into the page, and that means that your fingers would curl around in a clockwise direction, and that's going to be representative of a negative torque. So the right-hand rule is something that we use a lot, especially in electromagnetism. And the reason that we use it there is because, again, this cross-product mathematical tool comes up again with dealing with vectors. So I encourage you strongly, if you want to know a little more about cross-product and dot product, I would certainly take a look at basic linear algebra information from a college course. So now we get to what equilibrium is all about. We've defined what torque was, and remember that our second condition of equilibrium is the fact that it is not accelerating angularly. And what that means is the net torque is going to have to be equal to zero. Because if it wasn't equal to zero, then we would have some sort of acceleration angularly, either clockwise or counterclockwise. And so because we've done all of this definition of direction, the key thing to remember here is once you determine whether you're calling something clockwise or counterclockwise, just make sure that you include all of the forces in the clockwise direction, all of the forces in the counterclockwise direction. The nice part is, even if you mistakenly call clockwise counterclockwise and vice versa, so long as you're consistent about which way you're pointing your vectors, you shouldn't go wrong. The key words here, though, is that the net torque is going to be zero. There is no change in the rate of rotation. It's either not rotating at all or it's rotating at a constant angular speed. So the key to all equilibrium problems is first trying to find a point of rotation and then drawing free body diagrams to represent all the forces at play. The mistake that a lot of students make when they deal with equilibrium problems is they think that they have enough information to solve it using either translational equilibrium or torques alone. And my advice to you is always look for torques and this idea of rotation first, and then whatever information you don't have, take a look at the translational equilibrium, and I'm sure you will be able to at least be able to build a system of equations that you'll be able to solve. So if we take a look at this example here, we see that there's a beam that's being held up by a wire, and there's a person standing on that beam. And so if we draw all the vectors, what you can see is we actually have four represented. we have the tension in the wire that's holding up the far right side of the beam. You have the 600 Newton force, which is pointing straight down. That's the weight of the person itself. And then you got that little 300 Newton force there. And what that is that's actually the weight of the beam itself. And how do we know where that is? Well, this beam looks awfully uniform to me. And if it's awfully uniform, that means that the weight of the beam can all be concentrated right at the center of its mass, which is going to be right smack dab in the middle of that beam. So I would say 95% of the questions you deal with are going to involve uniform beams of some kind. However, if they're not uniform, you're going to have to go ahead and calculate the center of mass or the center of gravity. There's another lesson for that that's going to come up in a couple lessons. But if you don't know how to do that already, trust the fact that for the most part, they're going to be uniform to start. The last vector, the one I haven't talked about yet, is that R vector at the origin point there. And that's an important thing to remember, because what a lot of people mistakenly think is because there's nothing listed about the hinge, that there must be no forces present. But that's absolutely not true, and there's two reasons why. The first one is if you take a look at the tension, you see that the tension is pulling in and to the left. Well, that means that this beam is being pushed in and to the left. And what's the wall doing to the hinge at that point? It's going to push back and to the right. And so now we've equated it because the wall is pushing back on the beam, which is being pushed in by the tension on the rope itself. The second one is that we have two vectors pointing down for weight, both of the beam and the person, and we have one component of the tension that would also be vertical. But chances are is that's not going to be sufficient for it to stay in equilibrium. Well, what that means is we also need another component, which is going to be the hinge's ability to keep it from falling down as well. And so the hardest questions that you see in this unit typically deal with having to find the actual force applied on the hinge itself. And that's because it's actually going to be some sort of vector that's going to be on an angle, and there's going to be definitely some trig and things like that you're going to have to deal with to get that vector right. So please be aware when you have questions that involve finding the force of the hinge. If we take a look at another one, the classic question that we involve with in equilibrium is this idea of a ladder problem. And the common mistake about ladder problems is people immediately think that this just must be a torque problem because, hey, if the wall wasn't there, this ladder would fall right down. And in some cases, you're going to need to deal with torque. But guess what? When we look at this question and we think about all the forces at play, the first thing to recognize is that at the top of the ladder, it's pushing in towards the wall, which means that there has to be a normal force pushing back. And that's going to be perpendicular to the surface by definition. Common mistake with ladder problems is people draw the normal force on a perpendicular angle to the ladder itself instead of the wall. The second thing to notice is that at the bottom, we can see that there is both a normal force and this force pointing in. Well, that's going to be the force of friction in this case, because if there wasn't friction pointing in, what would the bottom of that ladder do? It would want to push out away from the wall. And so friction's job there is to keep that ladder up at the angle that it is. There could be questions that involve dealing with friction along the wall itself, but if that's the case, they're going to have to give you some information about the coefficient of friction along that wall that you'll have to deal with. Most ladder problems deal with the wall being frictionless and the floor or the ground having some sort of coefficient of friction. The final thing to recognize again is that the weight of the ladder is going to matter. And again, it will be uniform almost always, which means that the weight of the ladder is going to be right smack dab in the middle of it, but it's going to be pointing straight down. Now, what a lot of people do is they start coming up with the idea of torques and angles and things like that. But if you look at this free body diagram, you can clearly see that everything is either in a vertical direction or a horizontal direction. And that's going to really help you try to solve these questions right away, because you're going to get to equate some quantities together, which hopefully leads to a better understanding of the solution you need to deal with. So ladder problems look intimidating at first, but those free body diagrams are going to be your key to success. Okay, so let's try an example problem. You see here that we're going back to this idea of a beam being held up by a wire and some sort of hinge on the wall. And the two questions being asked are the classic questions here, which is what is the tension in the cable and what is the magnitude of the force being exerted on the beam by the building. Don't misunderstand this to mean something like the normal force. If we're talking about the magnitude of the force exerted on the beam by the building, that means that there's going to be this horizontal component and vertical component to deal with. The other key here is the fact that it asks for the magnitude implies that there was probably some sort of angle that you could calculate as well, but it's beyond the scope of this question. So don't be scared of a question like this, but don't underestimate this question in the difficulty that it's going to have. Now you can see here that they give you a couple of different things. They tell you the weights in newtons, and that's a key thing to remember here. We don't need something in kilograms. If they give it to us in newtons, thank you very much, they've done a calculation for us. The other thing that they typically do on diagrams is they give us distances, but then they'll also give us other distances, and they'll either label it directly from some point or they won't. And if they do label it from some point directly, that point typically is going to be your point of rotation or your origin point that you're going to use. So look at the diagrams of your questions and hopefully it gives you a hint as to where you have to go. Okay, so to answer our first question here about the tension in the cable, the first thing we have to do is go back to the free body diagram that we made before. And the key thing to remember here is that we have this big ugly vector that's r that we don't have any information about quite yet. And if we focus purely on translational equilibrium, we would have a lot of equations with a lot of unknowns that we wouldn't be able to solve quite yet. However, if we make that point, the hinge, a rotation point, when you think about what our definition of torque is, we know that torque is based upon the distance away from the origin point. Well, if we have an origin point right at a vector that we don't know the answer to, then that essentially eliminates that vector from the calculation of something else. So when we have too many unknowns, the key feature here is to go to torque first. And if we make that point at where r is coming from, our rotation point, that r vector doesn't have to be known for us to be able to solve for something like the tension. And so you can see here that what we've done is we've taken the sum of the three torques, which in this case is the torque of the beam, which is going to be down, and we're going to call that clockwise, plus the torque of the man actually standing on the beam, which is also going to be down or clockwise. And we're going to subtract from that now the torque caused by the tension itself, which is going to be counterclockwise, and that has to be equal to 0. Now, another way you could do this is just say the sum of the beam and man's torque has to be equal to the torque caused by the cable, and you could solve that way too. But this is just an easy way to see that the net torque in this case is equal to 0. From there, we can substitute in the quantities that we know. And you'll notice that when we are dealing with the tension now, we're only dealing with the perpendicular component because we've taken t sine theta and input it, not just t. That's a key mistake that many people make. With this equation now, we can actually solve for t, substitute in your numbers, and you end up with a value of 416 newtons. Now, something very important is listed here that you may not see immediately, and that comes with the units of distance itself. And you can see that we have meters on the top and meters on the bottom, which means they actually cancel out. Well, that's exactly what they should do, but it also means that if we hadn't had these in meters, let's say we had these in centimeters, the actual units for distance would still cancel out, and you would still get the appropriate answer. I would encourage you strongly to convert everything into SI units. However, you can get lucky in that even if you have the wrong distance units, so long as they're all the same wrong distance units, mathematically you can end up with the right answer. For the second question now, we're going to go ahead and go to translational equilibrium. And when we do so, remember, we're going to split this up in terms of the x direction and the y direction. So in the x direction, we know that the only component available is the horizontal component caused by the tension, which means that the x component of our vector r has to be equivalent to this component of tension. And when we calculate that, we get a value of 238 newtons. The exact same thing can be done in the case of the vertical components because, again, we have the y component of r, we have the y component of the tension, and then we have the forces caused by the man and the beam itself, which were already vertical to begin with. And so when we do this sum, we can very quickly come up with a y component for r to be 624 newtons. Now, one key thing to remember when you're doing these kinds of questions is don't get caught multiplying things by the distance away from the rotation point. You've already dealt with that to find what the tension was to begin with. Now you're using the components and you're using the vertical and horizontal components, this whole idea of translational equilibrium, to figure out the rest of the forces at play. So don't get caught doing torque type calculations when we're really just dealing with the sum or the difference of forces. Now that we have our x component and our y component, we simply use the Pythagorean theorem to come up with the magnitude as 668 newtons. If you had to find the angle, you would simply use some sort of trig function related to either the y and the x or the y and the hypotenuse, pretty much anything you want, because you have all three sides of the triangle. So keep in mind, please, that we dealt with torque to find the tension and then translational equilibrium to find the actual force caused by the wall on the beam itself. The second example problem we'll deal with is the classic ladder problem. And in this case, you can see that a ladder is leaning against a wall. We have the length of the ladder, we have the angle that it's on, and we know that it's frictionless on the wall, but there's some friction on the ground. And the classic questions that are asked for this are, what are the forces acting on the bottom of the ladder, and what is the coefficient of friction on the bottom of the ladder with the ground? So classic question, because again, if we're looking for the force on the bottom, that's going to lead us to the coefficient of friction as a result. So it's very much leading you through this problem and way of thinking. So to begin to answer our first question, the first thing we have to do is recognize the free body diagram yet again. And what you can see is that we have forces in the x direction and forces in the y direction. And it's key to note that because there's no friction on the wall, we don't label any friction there. And the other thing is, look at the normal forces with the ladder interacting with the frictionless wall and the ladder interacting with the ground. They both are perpendicular to the floor and not the ladder itself. And that's a key mistake that a lot of people make, is they think that because we're dealing with ladders and we're dealing with angles, that we have to find the perpendicular component. In this case, because we have labeled everything appropriately and because things are either horizontal or vertical, these are the only forces at play, and this is the proper directions that we have. So these three forces that I have listed here are absolutely the correct forces to use moving forward. You can see why ladder problems now can be a bit tricky, because people immediately want to go to torque when translational equilibrium is actually the best way to start. So now that we know that, we can actually take a look at this from a mathematical standpoint. And we know that because the only components in the horizontal direction are the normal force at the top and the force of friction pointing in so that the bottom of that ladder doesn't slide out from the wall, then F, lowercase f, the force of friction, has to be equal to that normal force. Conversely, if we take a look at the vertical, we can see that the weight of the ladder is pointing straight down. And we have this normal force that's pointing straight up, but because there's no other vertical forces present, the only force that is causing this normal force, F1, is the force of the ladder itself, the weight of the ladder. And so in that case, we have our first calculated total, which is that F1 is equal to 250 newtons, which is just the weight of the ladder itself. And it's important that when you actually formulate your solutions, that you clearly show this progression of understanding. If you just simply say that F1 is equal to 250 newtons, if I'm your teacher, I'm writing down, well, why? And you would have to explain yourself. And this is the basic way to explain why it is what it is. So again, we've gone translational to find what that force is. To find the second force, though, we're going to have to go ahead and go to rotation. And for that, we have to deal with the sum of the torques. And so really there's two torques at play here, and that has to do with the weight of the ladder and the normal force being caused by the interaction of the ladder at the top. And so our pivot point in this case is going to be right down on the ground where the ladder interacts with the ground that has friction. And the reason for that is simple. We don't know what the force of friction is yet. But when we put our pivot point there and we measure all of our position vectors from it, you can see pretty clearly that now we have the ability to solve for F2 directly, knowing all the other quantities. This is where we're actually going to have to find the components of FL and F2, because now we're dealing with a torque situation, which means we have to find those perpendicular components. And so what you see now is when I do the torque of the ladder, I'm going to take F2 and I'm actually going to multiply it by the cosine of phi in this case, which is just going to be the angle that's given. And then when I do the weight of the ladder, I'm going to multiply that by cosine of theta so that I, again, can get the second component. Now, why have I labeled these as two different angles? Because in this case, we have 58 degrees at the bottom, but that's actually only going to be representative of the angle between the ladder and its component. As opposed to the top, you can see that it's a much smaller angle. It's actually going to be the complementary angle to that. So be careful with your angular proofs here. It's pretty obvious to see that there's a right triangle between FL, the ladder, and the ground, and you can pretty easily go from 58 to 32 back to 58 again between FL and its component. So now that we have the trig done, we can solve for F2 directly. And now notice that the distances are all measured from the pivot point. It's from that origin point. You get to choose where that is, and it makes the most sense for it to be at the bottom because it was an unknown variable that we couldn't yet solve for. So it makes sense to make it a distance of 0 away from the pivot point so that it essentially eliminates itself from the calculation. Now we have this equation, we substitute in the values we have, and we end up with an answer of 78.1 newtons. A word to the wise, my friends, these distances aren't always given. What they might tell you is that the ladder is a length L, and that it is a uniform ladder, which means that it wouldn't have mattered that it was 6 meters or 12 meters. It would have been L and L over 2. But what would have happened is, within that equation, we still would have had the case where L over 2 was up top, L was on the bottom, the L would have canceled, so it really didn't matter that it was a length of 12 meters. What mattered is that the center of gravity, or the center of mass, was exactly right in the middle. So watch out for those ones where they don't give you the distance. All that means is, like anything else in physics, it's going to cancel out somewhere. So we've done it, folks. We've calculated F2, which means if we want to find the coefficient of friction, we already did an equality that F2 was equal to lowercase f, which we've labeled as the force of friction. And we know that's equal to mu Fn, or in this case, I've put it as a lowercase n. And so to find mu, the only equation we ever use to find mu, it's simply the force of friction divided by the normal force. We've already, from previous calculations, figured out that the normal force was equal to the weight of the ladder and that the force of friction was equal to F2, which we went through some translational and rotational equilibrium scenarios to get us the value 78.1. And in doing so, we can now find out that the coefficient of friction is going to be 0.312. So ladder problems look scary to begin with, and when you do the free body diagram, it can look even worse. But when you really break it down into translational and rotational situations, what you end up with is hopefully a fairly straightforward mathematical equation with some pretty hefty physics to get you there first. So folks, that's it for the idea of static and dynamic equilibrium. You'll notice that in my examples, I only used the case where they were stationary. It really wouldn't matter to say it's a beam sitting in a truck that's moving at a constant speed, because all of the mathematics you would do would be the exact same, and all the physical principles that we would use would be based on that, because the net force and the net torque still have to be 0 in those cases. So good luck to you with your practice problems, and we will see you again.